Hello everyone, welcome to the new lecture which is lecture number 3 of strength of material. So in this lecture we are going to study about axial stress and deformation. So basically we'll be doing the topics which are Hooke's law, superposition, deformation of axially loaded member. So today we'll be covering these topics. So currently where are we now? So, we have studied that stress is equal to P upon A, force per unit area, and we also have studied that the strain is nothing but change in length upon original length, right? So, then we know that applied load is P here and the area is A. So can we find out the elongation from this data? Like we have given P and A. So can we find out the elongation, or that means can we find out the delta L from this data? So stress is a different quantity, strain is a different quantity. Now we want to relate it, and we have been given the force which is applied. We have been given the area which is on which the force is applied. Now, given these two quantities only, can I calculate the change in length? Yes. So there comes the quantity that we call as Hooke's law, by which we relate stress and strain. So stress and strain can be related. So these are by Hooke's law. So we come to Hooke's law. So what's Hooke's law? So it is nothing but simply a relationship between stress and strain. So we can say sigma is inversely proportional to the strain. Stress is directly proportional to the strain, and if I remove this directly proportional sign, I get that stress, I will be putting equal to sign, and then I'll be putting one constant. So that constant is E, and E is nothing but Young's modulus. Okay, so we call it as Young's modulus. So from here I can also say that uh, this is only valid because it's directly proportional, right? So and E is here, I can say that it's a linear relation, right? So it's only valid for linear region, right? So here one constraint is that Hooke's law is not valid everywhere on the stress strain curve. We saw the stress strain curve, right? Somewhat like this, and then right. So it will be only valid. It will not be valid for like the region which are here, this area, but it will be valid till a linear region because there is a linear relationship between them, right? So this is what Hooke's law is. And yeah, so the question comes to our mind that how can I write E, from where this E appears. So if I see from the relation that I calculated earlier, this is nothing but stress upon strain, right? So E, from where this E came? So E is nothing but stress upon strain, and I can say from the graph, so the linear region, right? So stress upon strain, that means this is sigma and this is strain. So if I'm doing sigma upon epsilon, is it nothing but the slope tan theta? So I can say that it's a slope. So E is nothing but E is the slope of stress strain curve till elastic region, right? Because that's the only one which is linear. So E is slope. So from where does it, why it came because it is the slope of the line, right? And we know in general the line equation is y is equal to mx plus c, and c is the intercept at y-axis, so it's meeting at 0, right? So c will be 0, and slope is nothing but sigma upon epsilon, so that is nothing but e, and x is epsilon, and y is stress. So here the relationship comes like that, and I told you that this is why it follows a linear equation. So from here there is, like, if I have two bars which are experiencing the same strain, for example I have this bar, and there is similar kind of bar, both are experiencing the same stress, so same load is applied on them, right? Now the material which has more E, so this is E1 and this is E2, both are of different material, cross sectional area same, load applied same. So if so the material which has more E, that undergoes smaller strain. So because same load is there, right? So same load, that means same stress. If stress is same, then I need to keep E and epsilon the combination also the same. So if E is more, then I need to have strain less. So for the same load, different materials can generate different stress strain depending on the type of material and that's modulus of elasticity. And one more thing, that modulus of elasticity is fixed for every material, so it's a number and it's fixed for every material. For example, that E is 2 into 10 to the power 5 uh, MPa for steel, so it is for steel. Okay, so here it's written that higher will be the E, greater will be stiffness, and then there will be smaller elastic deformation. That means E more will give the strain less, right? So from here we can conclude this point, right? Now can we move on to next question, next slide, which is now from Hooke's law to we will be moving to deformation. So this is probably the most important derivation in this lecture. Now I want to calculate from Hooke's law the deformation value, right? So we have sigma, which is E upon epsilon, right? And sigma we know that it is P by A, and epsilon also I know. So can I put delta L upon L? Should I put everything at the one place? Deformation is nothing but delta L, right? Change in length. So can I know that change in length is nothing but P into L upon A into E. So this is the deformation. So we calculated from Hooke's law what will be the deformation value. So from here I can have certain results, like if force is applied is more, we'll be getting uh, deformation, more deformation. If I have length that is more, I'll be getting more deformation in that. So if a smaller length subject is there, and if there is another subject which is of longer length, then deformation in the longer one will be more. Okay, and if area is more, then I can say that deformation will be less, because these are inversely related. And if the modulus of elasticity is more, then also deformation will be less. This we discussed previously also, right? So we can interpret these many results from a single formula. So this is very important formula, we should remember it. Deformation is nothing but PL upon AE. Okay, now can we move to next, which is what controls this axial deformation? So we calculated the formula for axial deformation. Now the things that calculate is load, right? Just now we discussed. Length also controls this, area also, Young's modulus also. So the long and thin members deform more, short and thick members deform less, right? So this is how we can uh, get the interpretation of what PL upon AE means. Now let's have one thought experiment that we are doing. So this is something like, okay, so this is the same thing. Now, if now I have already explained you, can you tell that which bar will elongate more? So we have bar A, which is long and thin, and then we have bar B, which is short and thick, right? So in our, from our previous discussion, we can directly say that the elongation in bar A will be more than bar B because of this relation, right? So this we already knew. So if the bars will be something like this, you will directly say that it is because of long and thin bar that is going to be deformed more. Now let's move on. So we have our next topic, which is superposition. So, we should learn about the principle of superposition. So, the question that comes to our mind when we want to know about superposition, that what if a member is subjected to more than one load? So, till now we are discussing that only one load is there, P. So due to that P load, there are things that is getting changed, right? There is elongation going on in that. But if there are more than one load, then can we say something? What will be the effect on this that material? So for that we have, can we calculate the combined effect? Will there be combined effect first of all? Yes. So there will be a combined effect, right? That combined effect will be how much? So as per the principle of superposition, principle of superposition, so as per this principle, we say that each of the loading will have their own effect, and the combined effect will be the summation of all the effects. Okay, so the deformation due to P1 plus deformation due to P2 plus deformation due to P3, so that will be the effect, that is the combined effect. So I can say that total response, right, will be equal to the summation of individual response, right? So this is what superposition principle means. So if some a body is uh, this is initial position and it has one load here, one load here, so the combined effect will be due to both the elongation, so we'll be adding that. So this is nothing but superposition, right? Now next, let's discuss one simple example for superposition. So imagine we have load P1. Okay, P1 produces L1 deformation and P2 produces L2 deformation, right? Then what will be the total deformation in that body? For example, like there is so we have something, some body like this. Okay, we have P1 here, we have P2 here. Now if I uh, make the deformation due to P1, so let's say due to P1 the deformation is something like this, and due to P2, P2 is here, so due to P2 the deformation is something like this. Okay, so what I'll be doing is, I'll be, this is del L1 del L2, so del L will be equal to del L1 plus del L2. So this is the effect of principle of superposition, and the thing is that it is valid only when the system behaves linearly only when system behaves linearly. If non-linear behavior is there, we will not be able to follow this principle of superposition. So for this, system should be under the linear conditions. Okay. So this is our one constraint in that. Now we have that when this superposition fails, okay, so it will not be directly applied when material is behaving as non-linear. Okay, in the non-linear region, load is that much that the stress strain goes into the non-linear region. In that region we can't apply. So the load should be in limited region in which it should be follow the linearity. Okay, and then that means large deformation effects become important, right? So large deformation effects, that means, so if smaller deformations are there, it will be good, but in larger deformation we need to have the more focus on that. And uh, so large deformation will happen when large stress is there, right? Large stress will be in the non-linear region. So again, this connects to this non-linearity only. And then plastic deformation occurs. Then also we can't use plastic deformation will also occur in non-linear region, right? And geometry load response changes significantly. That means you are putting some load and then removing that, putting higher load, removing that, putting lower load, removing that, so that your load is changing again and again. So in that case also superposition will fail. Okay, so this is what superposition uh, means. Now can we go to next? So we can say that one point, that linearity is the key here. So it will only work in linear region. So till now we saw Hooke's law working in linear region, and then we saw the deformation that also working in linear region, and then now we saw the superposition principle. It is also working in linear region. So these all are working in linear region of the stress strain curve of the material which is asked to calculate. Okay. Now let's say the deformation of an axially loaded member. So we have a basic axially loaded member. That means we have some one member something like this, and we it is axially loaded. Okay, this is its axis. So on that axis it is loaded. So that means it is axially loaded. L is the length, A is the area, E is the Young's modulus, and P is the force which is on this member. So from here we calculated earlier that it is PL upon AE, right? But can we know that what assumptions we made for this? I mean, so there should be some assumptions, right? Because this will not follow in every region. So the first assumption was that we'll be working only in the linear region, right? That was the very first assumption here. So assumptions behind this deformation formula is, first of all, the bar should be prismatic and uniform everywhere. See, this is a non-uniform bar, right? So I have something like this. So this is a non-uniform bar. So in these kind of bar, we can't directly apply PL upon AE. Bar should be uniform, prismatic, and then assumption, constant cross sectional area. See, non-uniform means that only here the cross sectional area will be this much big, and here the cross sectional area will be this much. So it is not constant, right? At every section the area will be different. So there should be assumption, second assumption is that it should be constant cross sectional area, and materials should be homogeneous everywhere. Material should be homogeneous. That means the E value, modulus of elasticity, will be same at every point. That only we want. If E also changes, this will not be valid, right? And then linear elastic behavior, that also because it came from Hooke's law, that is working in linearity. And then load should be axial, deformation should be small, and load applied along centroidal axis only. So load, first of all, this is axis. So load is applied axially, uh, and it is in the axial direction. We can't apply load somewhere like here or here, right? So it's these loads are in the direction of axis, but not at the point of centroid of the axis. So this also we should take care. So these are the assumptions behind PL upon AE, right? Now let's move on to next, which is, now can we have the general axial deformation formula, because that is a specific that's working in the linear region. Now if I want to calculate the general formula, so can I calculate that? Yes. So from that thing only we can calculate the general area. So generalized form can be like, I have d of dl is nothing but p of x. So it's a function of x. With the distance the bar is changing, right? So force is also changing at every point, and area is also changing, right? Area is also function of x. And then we have length, modulus of elasticity, because it's the material becomes non-homogeneous, so E also becomes the function of x. And then L is nothing but dx, length, right? So this is the general deformation formula. And if I want to remove this d sign, I can integrate, right? So if I integrate this d del l, this whole up to dx, so this will be like delta l, full dl I had integrated, so this will be delta l, and p, and then I'll be from 0 to l, length of bar, this is 0 and this is l. So from 0 to l, you will be having p as a function of x, a as a function of x, e as a function of x, and dx. So if you calculate, uh, integrate after these values, putting in the function of x, then I can get the general deformation. So with this, this is the general deformation formula. Now in the later sections, we'll be discussing, we'll be asked to calculate the stepped bars, and we'll be asked to calculate the deformation into the tapered bars. The bar I made previously, that was tapered. And then we can also can calculate composite bars, and we can also calculate the self weight of the bar. Okay, so these will be discussing later. Okay, so this is the general axial formula. From this I'll be calculating all these four type of formulas separately. Okay, now, so now we should know uniform versus non-uniform member or the bar. Okay, so we have uniform bar, which for which we have delta L is equal to PL upon AE. And for non-uniform bar, we have delta L, that is nothing but integration of Px, Ax, Ex into dx. Okay, so the familiar PL upon AE equation is actually a special case. This is a special case of this non-uniform bar. This is the generalized case, right? So non-uniform is a generalized case, out of which there is a one special case which becomes for uniform, that gives the formula as PL upon AE, because everywhere the area and length is same. So we'll be putting like this in the uniform bar. So the PL upon AE equation is actually a special case of the generalized deformation equation, right? So It's a very good concept here. Now we have the internal force connection. So external load will not always be equal to P. Now what does that mean? So see, so we have here that in a member with multiple axis loads, the internal axial force of a section NX is not necessarily equal to any single external loads. That means we have one example here in which I have this 20 kilonewton, and then internally here also I applied one 30 kilonewton load, and there I applied one 40 kilonewton load, and then 10 kilonewton load. Okay, like this. Now total length is this, and at every length we have applied the load. So I need to check the equilibrium. So here take rightward positive. So rightwards are positive, that means 30 positive, 10 positive, 20 negative, 40 negative. So equilibrium should be checked. The summation of all forces in any single direction should be 0. That is equilibrium. So if I added all the forces, so delta F came 0. That means the member is in equilibrium. Okay, that means it will not move. Okay, because it's in equilibrium. Now if we make a cut at different section. So the first cut we made at this point, right? So only 20 kilonewton load is there. So at this point the value of Nx will be from the equilibrium. Nx will also come to be as 20 kilonewton in tension, right? Now if I make a cut at this location, right? So 20 kilonewton in this direction, 30 kilonewton in this direction, what will be the value of Nx? So Nx came out to be minus 20 and plus 30, so it came out to be minus 10. Minus 10 means the minus sign says that whatever sign we assume, that is intention, so it's not intention, it's opposite of that, so that's why it became compression. Now if I want to see it here, if I made a cut at this position, so it is 20, 30, 40. So if I added, this is plus 30 minus 40 minus 20, it came as minus 30, which will go on that side and will become plus 30. That means the assumed direction is same as the final answer. So it is in tension. So can you see the internal load which is coming at every section is different, right? So this is our key takeaway, that the internal axial force at a section depends on all external loads on one side of the section, not the other side, one side. Okay, the same case will come if I assume this side of the load also. Okay, it will not come as different value, you can check it. Okay, now Nx changes from segment to segment. Yes, and always Nx first before using. Uh, we have to find this Nx always before using this sigma is equal to f upon 8 or deformation. So we have to, at every place there will be different deformation. So if if we calculate the axial force diagram, so it will be something like this: plus 20 minus 10 plus 30. So this is what the internal force connection is, right? So can we have one numerical? So let's say we have a basic bar. The bar is of force as 50 kilonewton. We have the length of the bar as 2 meter. We have the area as 500 mm square, and we have modulus of elasticity or Young's modulus as 200 gigapascal. We need to find the elongation, so it's easy, right? So calculate it and tell me the answer in comments. So PL upon AE. The thing is that we need to homogenize the units. So whatever, so values calculation is very easy, but the unit homogenization is tough. So you have to make the thing in proper similar units. Okay, so try it and you can do it. It's a easy numerical. Now we have, okay, so I have few questions for you, like, so answer it in comments below. If length doubles, what happens to elongation? If area doubles, what happens to elongation? And if Young's modulus doubles, what will happen? And can we use the superposition after yielding? You can tell me this also. Why can't PL upon AE always be used for taper bar? This also you can answer. And what is the difference between external load P and internal axial force Nx? I hope if this lecture you got to understand properly, you will be able to answer all the questions. These are easy questions. So in the gate, you will be getting questions with these kind of conceptual values. So it can be in the uh, objective type 1 mark question. So this is the basic concept. I guess you understood. Now we'll be meeting in the next lecture.